to.
Oh, no. Okay, everyone. It is my pleasure to introduce our great lecturer for today. This is Dr. Adam Kraus. So Adam came, he got his Ph.D. from Caltech. He's got like all the fellowships. So he got Hubble Fellowship, got the Clay Fellowship. He probably got some he had to turn down, but these are the most prestigious fellowships in the field. Spent some time in Harvard. It was too cold, and then we got him here in 2013. And when we got him, so the field of exoplanets and star formation, you know, they were around, but they were just starting to come up and become extremely important. We had already had a presence here, and we realized how important it was for the future. And so Adam was one of our first hires. And we hired him with the intention of starting a group of star formation linked to planet formation and that worked extremely well. And we've been very pleased since. He has a huge group of people working for him, and I do not know how he keeps track of them. It not only that they love working in his group. And so he's fantastic in terms of mentoring, fantastic in terms of teaching. He teaches a class on the movie Interstellar, which I want to take sometime. And one thing that I just now, being chair, I realized, you know, you ask a faculty to do something and they often just say, yeah, sure, I'll do it. And then like, they never do it. And you got to do it yourself. Not Adam. Adam is one of the best, if not the best that I know in terms of support for the department activities. And so I'm delighted to have Adam talk about his work in planets and star formation. So Adam.
Okay, thanks, Carl. So I'm glad to be here with everyone, so thank you for joining us. I do also want to welcome everyone who's online. They haven't told me the final head count. I guess I'll find out afterward. But this is part of the Texas Science Festival, and so we're being joined by members of the public and also apparently by future Longhorns who are trying to decide where they're going to go to school next year. And so yeah, I definitely look forward to hearing everyone's questions after the talk, both in the room and I think we have it set up to get questions from online potentially. So today, I'm going to be telling you about the story of planetary systems around other stars and how you go from the earliest stages of building a new planet, from a cloud of gas and dust out in space to what you see around us here, to an Earth, or to planets that are very unlike Earth. And I do want to start by calling out the members of my research group. So they do most of the real work, probably all of the real work for your precise definitions. But the graduate students and postdocs who have been working with me have been instrumental to all of the things that we've done. And so I particularly want to say, look for their pictures to appear in the upper corner of results as I'm talking through this, so you can see who is responsible for this, either direct group members or the first of their students are now going to do a few call outs for those who have now gone on elsewhere and become professors at other universities. So I want to start with how we have mostly found planets around other stars. And our field started with the radial velocity planet search method. And the idea here is straightforward. You have a planet going in orbit around its star, but because the planet has mass and the star has mass, the star is also going in an orbit around the center of mass between the two. And we see the star's motion forward and back. If we were to measure the velocity of the star as via the Doppler shift of its spectrum, we can say if there's a planet there. And we can get the planet mass, for example, through this method. This was really where planets started. And of course, Bill Cochran, who's here with us, was one of the instrumental people in really pursuing this method for the first 10, 15 years of exoplanet science. Today, another method, the transiting exoplanet search method, has now really taken off and is discovering most of the planets that we're finding. And here, it's also a very simple cartoon picture to look at. You have a star, you have a planet going in orbit around that star. I like this movie because it repeats about often enough to do the "you're getting very sleepy now" thing, except for right after lunch, so I don't want to lean into that too much. But the idea is it's going around, and every once in a while, for some fraction of planets, they're going to pass along our line of sight, or maybe above or maybe below for most, but some will pass between, block a little bit of the light, and we did a dip. If we just watch a bunch of stars and measure their brightness over time and look for the dips, then we will see, oh, the star here is at a certain brightness, it dips for a bit, it stays fainter for as long as the planet takes to pass in front, and then the planet passes and it goes back to its original brightness. And here, the depth of this tells us the planet's size, or the planet radius. And then, in both of those methods, the repetition tells us what's the orbital period, or what's the orbital radius. How far out from the star is the planet? And in terms of using methods like this, and I'm going to talk mostly about the transit method for today, then a lot of what we're going to talk about is coming from space telescopes. And I really feel like in terms of thinking about this like a story, then I kind of feel like we've gotten an image of or we've gotten a view of what the last chapter of the story of planet evolution is. So like the Kepler Space Telescope has found 4,000 planets over its original mission. It spent 4 years watching the same patch of sky, just waiting for transits, waiting for dips on a couple 100,000 stars. And it found 4,000 planets crossing the stars in that field. And so this orients you for those who know the night sky well. Basically, it was this patch not too far off the galactic plane, near the constellation of Cygnus, also near Lyra's nearby, Aquila, etc. And so it just stared at that patch of sky that's the size of your open hand at arm's length, more or less, for 4 years. And it revealed what are the final products of planetary evolution. Because these are mostly old stars in here. They deliberately chose a place that was representative of the entire Milky Way to get an average answer of what planets are out there. But at least for my purposes, then there was a drawback to that, which was there weren't any of the interesting like niche environments that we need to reassemble the rest of the story. So to demonstrate what Kepler has told us, then I can give you sort of the scientist's view, which is, and now also what RVs have shown us. This is a plot of planet mass against planet orbital period that was generated a couple weeks ago now out of the Exoplanet archive that NASA runs. And the points show you all of the planets that we found around other stars. And here and on the next plot, I've shown Earth and Neptune and Jupiter just to reinforce where they fall at here. You might notice that they're on the edges of what we can see right now, which is an interesting other story. So we can think about this in terms of mass versus orbital period for planets that have been observed via the RV method or other ways that give you mass, or planet size or radius versus orbital period. And again, the same planets outlined. And there are thousands of points here. So the punchline to take away from this is we've gotten a really good picture of planetary systems, but like points can only, on a scatter plot, can only take you so far. I really like that there's a visceral way of visualizing this, where someone compiled what's called the Kepler orrery. These are all of the multi-planet systems that Kepler found. And it's going to start zooming out here shortly. They didn't bother plotting the systems with just one planet going around a star. So these are all systems with 2 or more planets, and the planets are scaled to each other. The orbit sizes are scaled to each other. They're not mutually the same scale. The sizes don't work out. And they're color-coded by the temperature of the surface. This tells you just how many planets we have to say, after billions of years, planetary systems end up looking like this. But then we've also gotten a pretty good view of sort of the prologue. If we want to think about this as a story, we've read the last chapter, we've read the prologue and maybe chapter 1. You might see where I'm going with some missing stuff in the middle. We can go and look at newly formed star clusters. We can look at molecular clouds. We can study star formation, like Matthew talked about this morning. And I showed this in part. I think Neil Evans, who's in the room, will probably recognize this. It came from his Spitzer program, Torres de Discs, studying what planet formation looked like using the Spitzer Space Telescope. So we can go image places where stars are forming and see clusters of stars that are newly forming or newly formed. We can also look more closely at them using observatories like ALMA, which is a radio observatory, to see that these newly formed stars are orbited by disks of dust and gas that are in the process of coalescing into planets. The question is, how can we connect across these chapters and go from here, this is the starting point, this is ages of 1 million years or millions of years, to the planets that we see with Kepler and with all the other planet search techniques we're using, and now with other space observatories that have ages of billions of years, 1,000 times longer. And so there's going to be a plot line here, and I'm going to outline the broad view of what we think it is. And it starts with actual star formation. So Matthew showed a capture out of this movie this morning, I think somewhere in here. Stella Offner would have shown it to you last year. And this is actually by a Hubble fellow who worked with Stella here at UT. And so this is showing the process of a cloud of gas and dust collapsing to form stars. And you get these complicated environments with lots of other young stars around, all forming at the same time. And maybe one takeaway to remember from this is that depending on the initial conditions, you get a wide range of different environments like this. This looks fairly dense to me from studying things in our local neighborhood that are mostly smaller and a little more sparse. But it's going to continue panning around and zooming in. But at the end, after about 10 million years or so, you're going to have a cluster of newly formed stars. And so this actually sets up a question, even initially, how does environment shape planetary systems? Even within one region, if you're in the core versus on the edge, does this change things? If you form in a really high mass cluster with a lot of stars or a lower mass one, how does that change your planetary story? The second part of the plot line is planets will form in those disks. And so this shows a movie of basically showing how circular the orbit is as a function of orbital radius for a bunch of small pieces like that early on in this disk, dust grains would have collided and stuck and grown fairly quickly to things the size of asteroids to Mars. And then there's a question on longer timescales. Time is ticking off up here in millions of years. Then how do you grow from there to planets? And so in this disk, you basically just say small particles collide and stick over and over again until eventually they grow into planets. And then we can ask things like, where do the planets form? Do they form close in, further out? What sets their size? What sets their composition? One bit of color coding in this movie is things close in are red, things that far out are blue. That's water content. There's more water far out where everything's cold enough for water to freeze out and form ice. Because then once you have ice particles, those can collide and stick, and your planet can have a substantial water budget. Close in, you can't. But then over time, as things end up interact with each other, kicking themselves onto stretched orbits, they'll mix inward and outward until maybe you can get water-rich planets closer in if you had the reservoir out there to start with. The third piece of this is after you've made your planets, they move around. And there's basically two routes that you can take to move your planet, we think. Either early on, then when you still have that disk of gas and dust that your planets are being built out of, once you build a planet, then it's going to interact with that disk. That's what this simulation here is showing, where if there's a planet here, then it's raising tidal structures, spiral structures in the disk. But then also that basically is creating asymmetries in the mass. So the planet's feeling a torque. It's feeling a slight pull backward in its orbit, which causes it to spiral gradually inward. This happens fast. By the time the disk is gone, this mechanism can't work anymore. But then on a slower pace, then planets can also interact with other planets or with distant stars, distant binary star companions. And so what happens is a planet that's initially here's to zoom in on the outer orbit and go to the inner orbit of a planet. And as the outer and inner orbits trade energy and angular momentum, then this orbit is going to shift around to stretch, return back to circular. It'll tilt itself around and return back. But the key is it can eventually get stretched enough that it starts interacting with the central star and tidally dumping energy into the star, which shrinks its orbit and moves it close in. So you basically have two routes to get planets close into their star, but operating on different time scales and also with questions of how often that should happen. Finally, the last piece of this story is that planets have atmospheres, and those atmospheres are going to evolve over time. Here, I'm actually showing a picture of our own sun. This is in the extreme UV from NASA's SOHO satellite. Keep an eye on here for I think in another 10 or 15 seconds, there's going to be something interesting happening. And this is our sun today. All that static is our sun reaching out to give Soho a hug, maybe not a friendly one, judging by all the static. But our sun, even today, is sitting there. It has star spots, it has flares, it has all sorts of features on its surface, and it's sending out high-energy particles. Young stars, in their first tens to hundreds of millions of years of life, will look like this, but in visible light. Like our sun looks reasonably quiet and boring, thankfully for us, in most of the light that it puts out. They're going to be doing this with far more energetic outbursts than the sun does. And so what happens is, if you start with an atmosphere, it might not stay the same, it might not stay, period. And so the idea is, and this was one of the big demographic results to come out of Kepler, is that if you think about basically a plot of the number of planets per star as a function of planet size, then you see actually two populations. There's a population that's a few times the size of Earth that we think look like Neptune's, and then there's a population that gets down to about the size of Earth that we think are more like Earth-type planets. And there's a gap in between them. And the thinking is that you probably start out with planets looking more like Neptune, and then over time, some fraction of them, even if they started with a hydrogen and helium atmosphere like Neptune's and smaller versions of Neptune do, and some fraction of times they'll lose it, or they'll at least lose some mass out of it in every case, and evolve to become smaller planets and maybe different planets. So the question is, how do planetary atmospheres evolve along with their star, as their star goes through its adolescence and quiets down? So we want to go back, and this is all rooted largely in our theoretical expectations of how the physics of a planetary system should play out over the tens to hundreds of millions of years to billions of years of its life. But we want to go back and actually catch this in action, because there are questions here. Are things fast or slow? How much do planet atmospheres evolve? Can we find ways to see differences in that evolution that we can tie back to the environmental conditions? And so my group enters this story actually not long after I came here, at a point where the field initially thought that we were in trouble, because in 2014, the Kepler Space Telescope lost multiple gyroscopes, and so it couldn't stabilize. It looked at one point in space for 4 years, but it couldn't point there for very long anymore, because it didn't have enough spinning gyroscopes at different orientations to maintain such a precise pointing. So everyone was very concerned and disappointed for a while, except then the creative engineers at NASA realized that they could play a fun game where basically if you turn your telescope the right way, one of the axes that it was not stable on can be stabilized using sunlight. So they turn it so the solar panels, which are symmetric, thankfully, are turned with the point of symmetry right toward the sun. And then the sunlight pushes evenly on both sides, but if it tilts one direction or the other, that becomes asymmetric, and there's more pressure on the side that rotated away, so it will return. So you can make up for losing one of those gyroscopes using the sun. You can only point in limited directions, and it turns out you also can't point in any one direction for very long, because eventually the orientations that have this work have you pointing at the sun if you wait longer than 90 days. But this meant they could create a new mission out of the same observatory, call it K2, and explore new environments beyond just the average, slightly boring part of the Milky Way that Kepler was observing, and look at new ages of stars, look at new galactic environments. And every 90 days, they would pick a field and look at it, then go to the next one, then go to the next one, then the next one, then the next one, turning as needed to avoid pointing at the sun and keep the solar panels lit. And so this was the point where I and one of the first people to join my group here, Andrew Mann, who was a Harlan J. Smith Fellow, who actually started at the same time as I did, started looking at this, and we said, okay, suddenly K2 is pointing at all these places where we know there are young stars, stars with definite ages, because there are star clusters there, for example. And so one of the early fields that was pointed at was the Hyades, which, to orient you, this is in the constellation of Taurus, maybe appropriately, and stars in the Hyades make up most of the horns of the bull. And so I appreciated that the first planet that Andrew found that had a set age was right next to the horns of the bull. So very, very university patriotic of him. And so the idea was, there's a star here that is a member of the High-D star cluster, about 700 million years old. The cartoon picture of what's happening there is this. There is a planet transiting across it, and K2 is measuring the brightness of this star over time. I'll note this is a fairly low mass star. It's a fair amount lower than the sun, about 0.3 times the mass of the sun. And there's a dip here. And the dip is about 1% in brightness, which is large on our scales. But you can do some of the math that I will spare you and figure out that this corresponds to a planet that's about 3.5 times the radius of Earth. It's a tiny bit smaller than Neptune, which is interesting to see. It's especially interesting to us because for such a low mass star, Kepler told us they don't have very many planets that are that much larger than Earth. So if we see a very large planet at young ages, this raises the possibility, are we starting to see evolution of atmospheres? Is this oversized, and over the next 4 billion years, then it would end up looking like the smaller, older siblings that Kepler found? Andrew also found another planet pretty soon after that. So this is K233, where this is actually in a much younger population called Upper Scorpius that's 10 million years old. So this is right after that planet formation process has ended. It's ended here. This star doesn't have a disk anymore, but it probably just got rid of it. And again, there's another planet here. It's about 5 Earth radii. And this was also a fairly small star, so it also looked big for what we would expect for other stars of similar size. And so at this age, then we could say, okay, there's another unusually large planet. Maybe we're starting to see a trend. It also orbits in just 5.5 days. So pretty early on, within 10 million years, then this planet has managed to get very close into its central star. This is far closer in than Mercury. And so this gave us the indication that some planets actually migrate inward very quickly. It doesn't take hundreds of millions of years or billions of years like interactions between planets or with a distant binary star would take. It got there during the time when the disk was there. So maybe we have the first indication of an answer. And so this process continued. It actually ended up requiring a lot of more sophisticated data analysis work as well. And so the activity of the stars, the fact that the stars are flaring and have such big star spots actually causes us big problems, because you'll see a movie playing here, and I'll probably get to it by the time it repeats. If this is the brightness of a typical star over time, then the variations here are on the order of a few percent up and down. That has nothing to do with dips due to planets. That's star spots on the star rotating in and out of view. Every once in a while, you'll see a flare, not so many on here. I think we'll see some later. And so the question is, if the star itself is varying in brightness like this, how do you see the dips? Maybe we drew helpful red lines, so that always really helps you to see the dips. But Aaron Rizzuto, another postdoc in my group, who was awarded a 51 Pegasi B fellowship while he was here, invented various methods, and I'm demonstrating the one down here that maybe we'll replay the movie, to basically fit this variability of the star and remove it. This is called notch filtering, where basically you just go along always asking, what's the best fit model for the stellar signal? And then if there's a transit there, can I draw just a notch and have it encompass the planet as well? Otherwise, you run the risk, if you try fitting out what the star is doing, you're going to subtract out what the planets are doing. And it works pretty well. For this system, there were 4 transits, and in all cases, this was what the brightness variation actually looked like. But then if you fit what the star is doing, subtract it off, you get this. You get a nice uniform dip in brightness that can tell us the properties of the planet. And so by the end of the K2 mission, which lasted about another 4 years before K2 ran out of propellant, then Andrew and Aaron and a few other collaborators working with us added more planets in the Hyades and other clusters like Chrysope or the Beehive, including a few more that are suspiciously large and one more that shrank onto its tiny orbit apparently pretty quickly. And so by the end of K2, the late 2010s, then we had a solid sample of planets where they had a definite age, because we knew what cluster they were in. We could look at the stars to say what the age was. So we could start mapping out the story of evolution over time. And a few that were even younger. Here, the color coding on this plot of planet radius and planet period. The color coding is how old they are, very young, very old. But most of the planets were the same adolescent age, around 600 to 700 million years old, because they mostly came from 2 clusters that happened to be that age. K2 could only look at a relatively small fraction of the Milky Way. So we needed more truly young planets to see more of this story than just if. So in my model for this, the purple points here are basically like the next to last chapter, or maybe the last few chapters of our story. But fortunately, NASA realized how wonderful this all has been for exoplanets, and approved another mission called Tess, the Transient Exoplanet Sky Survey, which is basically an all-sky Kepler. And so the movie here is showing you what the Tess satellite actually does. Every month, it's going around and observing a new, fairly large chunk of the sky, so that over 2 years, its first 2 years, it basically mapped most of the sky. And I'll note this square here is the Kepler field. So Tess has allowed us to look across a tremendously wider view, and by now, there were some gaps after 2 years, they've basically filled them in. So we've been able to search the entire sky. And any place where there's an interesting stellar population, for my purposes, young stars or stars with known ages, where we could look for planets. And so this was the point where Andrew and some of our other collaborators we all got together and said, okay, this calls for a new survey. Let's start a survey called TIME. Tess Hunt for Young and Maturing Exoplanets. Andrew's good with acronyms. His K2 one was ZITE, Zodiacal Exoplanets in Time. There are going to be a lot of ways to ride this for a while, I think, and Andrew's very inventive. And so we could go and say, oh, is there a young star population here? Let's wait until Tess observes it and then look for the planets, or here, or here. And it's being used for all sorts of other studies in exoplanets and in stellar astrophysics as well. And so we started finding more planets, and I'm going to show you a summary of the planets so far. But we also realized that we needed to bring more tools to bear on this, one of which fortunately launched around the same time, and that's the Gaia spacecraft. Because we realized, for example, there are a lot of stars out there where NASA was finding planets around them, and we looked at the star and said, that looks kind of young, but it's not part of a known cluster. So we said, okay, well, we think stars form in clusters, so there's probably a cluster there. Let's go look for it. And so this is a result with Ben Toffelmeyer, another postdoc in my group, who was also awarded a 51 Pi Psi B fellowship while he was here, where we basically went and said, okay, there's a star here. It has a transiting planet. This is the transit. It looks like it's young. Let's look around it for other stars that are moving through space, that are about the same distance away from us and moving through space with the same velocity and direction. This is what Gaia tells us. Gaia measures positions of stars very precisely, and by doing it over and over again, it can tell us how are they moving across the sky. And we found across an area that this whole plot is like something like that wide on the sky. There are less than 100 stars that are moving along with it through space. But that's enough for us to say this is a sparse scattering of stars that formed, in this case, it was about 250 million years ago, and are now just moving through the Milky Way, gradually dispersing. And we could use all of them to tell us what is the age of this one star, and therefore what's the age of its planet. We can say, what was the environment it formed in? This thing is pretty sparse compared to the Hyades, or even compared to that simulation that I ran from David Dusanoff earlier in this talk. And so we started naming these. The first one is Melange 1. We're up to Melange 7 or 8, and I've seen paper drafts with 9 and 10. So finding populations where we find a planet, say this is young, we just need to figure out what is its home, and then we find the home. Don't ask me what that acronym is. I wrote it in the notes, but it's, yeah, a little tortured. But also, even beyond saying, there's a planet here that we can find via standard planet search techniques. Now let's look for the star cluster home for it. We'd also go around and start systematically mapping more of the Milky Way to find these groups and specifically say, let's look for planets here or here or here. And this was the PhD thesis work of Ronan Kerr, who is now a Dunlap postdoctoral fellow up at the University of Toronto. So what he did is he used Gaia, which told us precise positions and velocities of stars, all the stars in the sky, down to a very faint level. He said, okay, let's find all the groups of them that are moving along together and are at the same distance, look for overdensities in the Milky Way's just population of stars, and map them out, and then go back and study those populations and figure out their ages. And he's actually basically reconstructing the star formation history of the Milky Way, or at least of our chunk of the Milky Way over the last 100 million years. So that's great for understanding star formation. It's great for starting the first context from the bottom up on galaxy evolution. But it also means that we have all of these huge populations to look for planets around. And so this is an example in the Cepheus-Hercules complex, which we didn't realize was there. It's only a few hundred parsecs, about 1,000 light years away, which is our backyard, and it has 20,000 stars. But we didn't know it was there until Gaia allowed us to go looking, and we saw, oh, across an area like that wide, there are 20,000 stars that are moving along with each other. And so this is a map of them. And this one I particularly liked because it actually overlaps with the original Kepler field. They chose the Kepler field originally to be boring because they wanted the average answer for the Milky Way. They didn't want anything weird to skew their average statement. This is what planets look like in our galaxy. But they didn't know what was there that was interesting. And now we can go back and say, oh, there was actually an interesting population. And so there are 4 planet hosts with 7 planets that Kepler found that now we can say, oh, those are actually young. And here's their age. And here's the environment that they formed in. We can also start follow-up on all of these planets that we're finding. And so this is actually work by a graduate student at the University of North Carolina working with Andrew Mann, Pachia Thao, who I'll note she was actually an undergraduate summer research intern here through the Taurus program in 2017, working with Andrew. So they started a very fruitful collaboration early. And so what Pachia is doing is using a method that's a variant on the transit planet search method called transmission spectroscopy. So the idea is you have a star, you have a planet passing in front. If you just measure the brightness of that star over time, you're gonna see a dip because the planet blocks some of the light. But if that planet has an atmosphere, and if that atmosphere is transparent at some wavelengths and opaque at others, you'll see a different depth based on which wavelength you look at. If you look at a wavelength where, for example, carbon dioxide or oxygen or water absorbs light, then the atmosphere will appear opaque, the planet will be bigger. In between, it'll be smaller. And so you can basically say, let's not just measure the brightness overall of the planet, but let's measure the brightness as a function of the color of the light coming through if I take a spectrum during transit and look for the differential depth at different wavelengths. You can basically say, and these are results out of the James Webb Space Telescope, taking spectra out in the infrared, where this is basically a measure of the planet depth. It's how big the planet appears at different wavelengths, across wavelengths from about 3 to 5 microns, so pretty far out in the infrared. These are some of the same wavelengths that Matthew was talking about this morning, where we see interesting evidence of molecules. And so we can use the fact that, for example, at this wavelength, the planet looks big. The dip was 0.6%. Here, it's only 0.4%. This is huge. This is 50% deeper, depending on which wavelength you look at. This is a surprisingly easy measurement to make. And we didn't quite expect that until we saw it. And then we said, oh yeah, actually, there's reasons to think about this that I might riff back on in a minute. But Pachia looked at this and said, okay, it's not just the same depth all the way across. This has an atmosphere. We're not surprised. This is actually more of a Jupiter-type planet, at least right now. But we see water, we see carbon dioxide, carbon monoxide. We actually see less common molecules, hydrogen sulfide, sulfur dioxide, et cetera. And so we can look at how the atmosphere evolves over time. And we're starting to see some things that they get made depending on what the star is doing, how much UV radiation is away from the star. And then they get destroyed. And so this also tells us how the planet's reacting to the star. But the newest result, and one I wanted to spend a little time on because it really is new, we published it in November, and it was an all-hands-on-deck exercise. I'll show you some of the McDonald hands that we turned to this. Was this new planet. It's around a young star. It's actually back in the Taurus constellation, so we are returning to the Bull for our latest headline result. But this is work by Madison Barber, led by Madison Barber, who's another graduate student at the University of North Carolina, working with Andrew, where she picked the acronym. So this system is TIDI-1. I don't recall the full acronym, so I could try to reconstruct it, but I might be wrong. But she found that there's a star there that has a dip that's recurring periodically. And so we can use that to say there is a planet going around this star. But it's a very complicated and interesting system. It's actually newly formed. It's only 3 million years old. I think depending on how you want to argue about stellar ages, it's the youngest planet that we've seen transiting. That's clearly a planet there. But it's accompanied, so this star has a transiting planet. It has a protoplanetary disk. We see the disk the planets are forming out of. And it has a distant binary companion. And the planet's bigger than Jupiter, which is an interesting thing that will be relevant in just a second. And so this is a sense of the geometry. You've got the star, you have the planet that's going more or less like this. You have a distant, I'll talk you through the geometry more. You have a distant binary companion, and you have the protoplanetary disk. So the question is, what type of planet is it? This was where we had to turn to McDonald to really get a sense of what's going on. And so we observed Tie-Dye 1 at McDonald with the Habitable Zone Planet Finder on HET. And this was director's time that we got pretty quickly last winter once we realized that this was interesting and that we wanted to observe it before it's set for the year. Where we got a bunch of velocity measurements, so using the RV planet search method, and showing here's the velocity, here's the orbital phase of the planet, and these are potential curves that we followed for different masses, 1.5 times Jupiter, Jupiter, or half of Jupiter. And there's no clear signature here of it following any of the curves that are at least this large. The limit there was actually something like about 1/4 of a Jupiter mass was our upper limit based on the data that would fit all of these velocity measurements, which is interesting because it's a Jupiter radius. And so we said, well, let's compare this to other planets, many old ones, but then also some young ones, and asked, okay, if this is the planet radius and this is the planet mass, these are all the planets where we've been able to measure that. Where does Tie-Dye 1 fall at? And it basically falls somewhere in this gap. It's too low of mass for its radius. Too low of density. So we're catching another planet that's very early on in its evolution, we assume, and it's going to be losing its atmosphere. I'll note this RV measurement's hard because the star is noisy, because it has all those flares and those spots going on. It's almost a worst case. So we're actually going to have to work really hard in order to figure out what the mass is. So that was our busy winter campaign for Tie-Dye 1. It was announced in November, but by that time, we had already started an intensive program looking at it because serendipitously, Tess was looking back at that same piece of sky in November to December. So I'm showing here, this is 10 days of test data. You can see variations of a few percent up and down just from the star. Also a nicely massive flare right in the middle of it. And so we said, we want to understand what the star is doing in order to know what it is doing to our velocity measurements of the star. And so we said, we want to observe it with Tess, which NASA did for a month. We used Las Cumbres Observatory, and most of the data came from its McDonald Observatory node, to take multicolor images. This is only one filter, and it's a very broad one, all of visible light. This allowed us to measure colors from the blue out to the near infrared. And there were something like 11,000 images taken. I think we used over 200 hours of LCO time on this one star. But it means that over the space of several months, we can map out this is the variation in brightness of the star, and we can use that to inform our measurement of what the star is doing, and therefore what our velocity measurements of the star will be. This is observations from the Hubble telescope with HPF. We observed it with 50 hours so far on HPF this season, getting velocity measurements of the star, looking for motion due to the planet. We see an interesting signal here, but that's what the star is actually doing. The amplitude here is like plus or minus 200 meters per second, give or take. A little less. But Danny Krolikowski, who was a graduate student with me using HPF to measure masses of young planets and to look for additional young planets in outer solar systems, he's been analyzing the data, and so he was able to model everything, and the modeling process is still underway. But we can say now that we're measuring a tentative detection that might turn into an even lower real number, or at least an even lower limit on the mass of only 30 times the mass of Earth. I'll note that is about right around 10% the mass of Jupiter, despite it still being a Jupiter radius. So this thing's really low density. So we can basically say this thing's the size of Jupiter. It's the mass of a Neptune, give or take. It might be less than that. This is a 2 sigma detection, which usually often ends up turning to an upper limit when we can get our modeling, when we can do more sophisticated modeling, and I don't have a deadline to talk about it. There's one other feature of this system, though, that's interesting, which is the tie-dye 1 system also has all these pieces, but their orientations are weird. So you have a planet, and it's orbiting edge on to us from our line of sight because it's blocking the light. The host star, we can look at its spectrum and measure the velocity spread in its spectrum and say it's orbiting equator on, so the planet and the star are aligned. That seems fine. The distant binary star, about 600 AU away, was actually serendipitously observed by me in 2009, and so I was able to go back and compare to that old data and say, can we see orbital motion? We can, and it's orbiting edge on, more or less. But the disk is tilted by over 60 degrees. So we're seeing weird evidence of dynamical interactions during the planet formation process, where initially I thought, oh, probably the disk was oriented along with the planets, but there was a distant binary star. Oh, before I measured the orbit, I was like, I bet it's tilted with respect to that. This happens when you're making a binary system. And so it like pulled the outer disk away. But no, everything's aligned except the disk. So either there are planet interactions going on in the outer system where we can't see the planets, or maybe there's something interesting about the history of how the mass from the broader cloud was accreted down to it. We're still sorting this out. So the question is, where are we today? And we're finding young planets at an ever-growing pace. We can see atmospheric evolution. We can see when planets migrate. This is an updated version of that summary plot. So planet radius, planet period, and color coding on the same age scale. We still have all of the dark points corresponding to adolescent planets, ages of 600 or 700 million years. But we're adding a lot that are younger, to 100 million years or less. And so we're sort of now asking, what are our next frontiers? Can we find more planets across a broader range of formation environments? When are we not finding planets? So we can get the most robust possible frequency measurements to compare directly to Kepler. What are the masses? What are they made of? And how are they evolving over time? And I do want to end with noting one other aspect of my group's work that has only recently looped back around, become relevant to this, to allow us to come at this from an unexpected angle. Because there's a shortcut here across this whole story we've been telling using binary star systems, which is actually where I started out. That's what I did my PhD thesis on, was looking for planets, not finding them, and then saying, I want to study binary star formation. And so the idea here is that if you look around the solar neighborhood, there are a lot of stars that are not just sitting there on their own. They have a companion, or more than one. Alpha Centauri, the closest sunlight star, actually has another star orbiting there that passes within like the distance for us, the distance out to Saturn. This probably changes the planet formation and planet evolution process. It certainly should change the environment. The majority of all stars like the sun are in binary systems, and they give us a unique opportunity to connect past and present. So this is another result from Ben Toffelmeyer, where he showed that binary stars actually change the formation environment dramatically. So this is a young binary system where we've measured the orbit of it. And the system basically has 2 stars, each has its disk. Astronomers have measured the orbit of it, and it's going something like this. And we can look at the disks and say, oh, look, these are actually small. That original image from ALMA I showed at the start would fill this entire field and more. So clearly what's happening is the binary companions are cutting off the outer parts of each other's disks. They only have tiny disks, their masses are small, their radii are small, they lack cold outer zones. The only stuff here that can be here is hot, because it's close in, within 5 or 10 times the Earth's orbital radius. This should change the future planets if compounds like water can never freeze out of the gas. They will just stay as a gas forever. There's no ice, there's no icy particles to get incorporated into your planets. So maybe you get like more rocky planets, or at least the same number, but you don't get as many that are made up of gases or ices or things like that. And in fact, you see precisely this. So these are recent results from a recent graduate student of mine, Kendall Sullivan, who's now a postdoc at Santa Cruz, where they showed that if you look at systems where there's another star within 100 AU, and this is number of planets as a function of planet size, you get plenty of things in the like 1 to 2 Earth radius range. These are like Earth, just a little bigger, but they're rocky. You don't get that many things. This is the blue curve here. You don't get that many things that are above about 2. that's where you start to be more Neptune-like. Whereas if you compare to the full sample of all planets we see out there, there's a balanced number of each. If you go to wide binaries, then you see all of them. You see Earths and you see Neptunes. So the idea here is when you have a close-in star, then you're tidally truncating the disk, and you're changing the mass budget or the mix of ingredients to make your planets. Truncate inside of a line where something freezes, and it will never freeze, so you can never have that thing be a solid to collide and stick with the Earth and give us some piece of our current chemical load. And so this is a route, we think, to controlled experiments on planet formation, where we can go and look at present-day binaries, say, what would it have done to the original disk, and then back out what was the complement, the mass and the chemical distribution we had to make them. And we're even seeing things where we see very wide binary systems. This is number of binary companions as a function of orbital radius. When we're surveying for planet hosting binaries out there, if you look at binaries wide about 1,000 AU, very wide, the planets are more common than they are in closer binaries or around single stars or just stars as a whole. This is an interesting sort of backward way of connecting the story, because we're looking at these and saying, if there was a binary companion at 1,000 AU or 10,000 AU away, it wouldn't survive in most clusters where stars are born. Stellar flybys would break that binary apart. So these have to have only formed in the very sparsest, lowest density environments. No nearby supernovae, no nearby high mass stars taking out ultraviolet light, no stellar flybys. So we have an environmental signature that apparently, if you're in a calm environment, you get more planets, which isn't surprising to us, but now we can make it quantitative and say how. So I want to wrap up here and leave you with a few takeaways. So we can track planet demographics across time. We can track those stories from the prologue of star formation and planet formation that we've been able to observe for several decades now, to the final chapter and epilogue of here are your planetary systems after 5 billion years. We can tell when planets shift their orbits around, it seems to be quickly. We can tell how long planets stay puffy, maybe up to 1 billion years, and we can even talk about what is the change in the composition that takes the form of being puffy versus evolving to their final atmospheres. In the future, we can start to test how planets are sculpted by binary stars, by supernovae, stellar flybys, et cetera, and using binary stars and using discoveries of more young planets, we have clear paths toward controlled experiments in planet formation, spanning across billions of years of history of the Milky Way. And with that, I would be happy to take any questions. Thank you.
Memo. Here's the mic.
Yeah.
Thank you.
Thank you, Adam. That was excellent. I have lots of questions, but let's see if any people in the audience have some questions. Go ahead.
I have two questions, if I may. All of the models that I've seen, and you had one here where the planet is rotating horizontally around the sun. Is there any likelihood that there is a perpendicular, a planet going perpendicular and not horizontal? Is that, and you detect that if that is the case?
So you can if you're lucky. If this is in the same system, then we think that planets should largely end up in the same orbital plane. I mean, tie-dye 1 is maybe making us question that to some extent. And there have been other reasons to question that in terms of looking at disks and seeing the more complicated structure. I think finding them becomes hard because if you want to see both planets, transits, it would have to be like tilted like this and like this. If it was tilted like this and like this, you wouldn't see a transit from the other planet. Radial velocities are easier. There was actually a result from here at UT, Barbara MacArthur and Fritz Benedict showed about 10, 15 years ago now, they were able to measure the position of stars on the sky and then also a radial velocity curve into all 3 dimensions and showed there was one planet orbiting like this and one like this. So you do get that, and we do see it sometimes. It's probably a sign that planets have interacted fairly strongly with each other along the way to kick each other out of calm alignment that we think should be the rule.
Okay, and one other question. As the planet orbits the sun, is there any indication that that planet has moons? Do you see just a steady flow across the sun, or little blips perhaps that are due to moons?
Yeah, so people have definitely looked for this. There have been controversial claims. I say controversial in terms of it's a hard measurement, not in terms of anything wrong was done. It's just, it's very hard to tell. What you basically have to do, the easy way, is you look for a transient planet, and then you look each time it crosses, is there another dip that's smaller, that sometimes will lead it, sometimes will lag it, because the moon is in orbit around the planet and will cross at a randomly selected time compared to when the planet does. So, and people have identified 1 or 2 cases where that might be happening, but you have to dig pretty far into the noise. And so it's a question of, are they removing all the instrumental systematics in order to dig out that signal? Or is this an instrumental systematic that they haven't been able to fully model yet? So they should be there, I would assume, judging by our own solar system, but it's going to be a hard detection.
Let me ask a question here. You had a couple plots that showed mass and against radius, and you had the Earth on there, and then you color coded by down to 100 million years. What's the expectation for what Earth would look like at 100 million years young?
So Earth specifically actually is maybe a special case because we think that's right around the time when we think the moon formed. Earth basically got sideswiped by something the size of Mars, and a large fraction of its crust and mantle at the time got knocked into space, and the proto-Mars, proto-Mars-like thing, basically coalesced with the Earth to make us. And then all the rest of the stuff, which was mostly rock, the lighter things, coalesced to make the moon. So at that point, our life was very exciting. For any other 100-million-year-old planet, on average, then it might be starting to solidify. It probably has a solid surface, but it still has to be very tectonically active because the middle's to be very hot. So if it has a crust, it's to be a very thin one, and probably a methane atmosphere, carbon dioxide, et cetera. You wouldn't want to breathe it.
So we are Martians then. Questions online? Oh.
We have one online. A parent asking on behalf of their 7-year-old daughter wants to know how you tell the age of a planet.
So telling the age of a planet, that is the hard piece here, because most of these methods we're talking about, we don't even see the planet. We see the planet's impact on the star. It's worth noting. We see the planet blocking light. We see the planet making the star move. So our strategy has usually been tell the age of the star, and then we know that planets form just after their stars form. And so to get the age of the star, there's a few different ways we can use it. Stars rotate, and they start out rotating fast, but they slow down over time. Basically, as they are rotating and kicking off flares and kicking out material, that material takes away angular momentum, spin, from the star. So the star spins more and more slowly over time. If we can measure the spin of the star, we can say roughly how old it is usually the technique that's used the most.
Additional questions? I'm just amazed that we are talking about these huge planet populations. That just blows me away every time I think about it. Okay. Well, thank you very much, Adam. It's excellent. And thank you all. We are done. And appreciate you coming here. And it's been great. Always enjoyed. Thank you all.
So if anybody needs a parking validation, you can visit our registration desk just outside these doors. Please, please, please make sure to grab one of these beautiful images that we have for you to take home with you with a little description on the back. So grab one of those before you go home. And save the date for our summer meeting, July 26th and 27th. And also, thank you, Cindy. Please return your lanyards at the registration desk. Oh, yeah. And if you want to take a beautiful floral arrangement home,